Welcome to all of you. Now we discuss competitive Lotka Volterra model in my mathematics paper D.Sc. 1 semester 5 B.Sc Honors Mathematics University of Calcutta. The population in competitive model, Lotka Volterra competitive model, interspecific competition. What is interspecific competition? It refers to the competition between two or more species for some limiting resource. This limiting resource can be food or nutrients, space, and mates, nesting sites, anything for which demand is greater than supply. When one species is a better competitor, interspecific competition negatively influences the other species by reducing population sizes and or growth rates, which in turn affects the population dynamics of the competitor. Here is the considered basic Lotka-Volterra competition model in which two species diminish each other per capita growth rate by inter-reference competition. Let the population densities of the species be N1 T and N2 T at any time T, and each species grows logistically in the absence of the other. So, and the model equations are this: 1 by N1 D N1 dt equal to R1, 1 minus N1 by K1 minus alpha 1 to N2 by K2 K1. Next, second equation: 1 by N2 dN2 dt R2, 1 minus N2 by K2 minus alpha 2 1 N1 by K2. Here K1, K2 are the carrying capacities of the two species. Alpha 1, 2 and 2, 1 represents this competition effects of species J on the species I. And Ri, R1 and R2 are the net growth rates of the species. First species is R1 and second species is R2. So this equation can be written as in this way: dN1 dt by this 2.1 and 2.2. Now first we discuss the simplest model for this uh, species competitive model, Lotka-Volterra competitive model. In the following Lotka-Volterra competitive model, dx dt, we place x for n1 and y for n2. X into 1 minus x minus alpha y dy dt equal to rho y 1 minus y beta x, where alpha, beta, rho are positive constants and xt and yt are the population sizes at time t. Then find the equilibrium points so that the coexistence equilibrium point is asymptotically stable for alpha less than 1 and beta less than 1, and unstable for alpha greater than 1 and beta greater than 1. Next, so that the second species will be surviving to its carrying capacity and the first species will be going to extinction for alpha greater than 1 and beta greater than 1. Now, we know that for critical points, equilibrium points or steady states, dx dt equals to 0 and dy dt equals to 0. Then dx dt equals to 0 gives x into 1 minus x minus alpha equals to 0, and rho y 1 minus y minus beta x is also equal to 0. And from this first equation, we get either x equal to 0 or 1 minus x minus alpha equal to 0. And from the second equation, we get either y equal to 0 or 1 minus y minus beta x equals to 0. Then from these we get 4 equilibrium points. 0, 0, 1, 0 is called E1, 0, 1 called E2, and E star, X star, Y star, where X star is the 1 minus alpha by 1 minus alpha beta, and Y star equals to 1 minus beta by 1 minus alpha beta. If we put x equal to 0 in this equation, 1 minus y minus beta into 0, so we get the value y equal to 1, and this point E2, 0, 1, 1. If we put y equal to 0 in this equation, then 1 minus x minus alpha into 0 equal to 0 gives x equal to 1, and we get the critical point E1, 1, 0. And solving these two equations, 1 minus x minus alpha equal to 0 and 1 minus y minus beta x equals to 0, by cross multiplication, we get x star 1 minus alpha by 1 minus alpha beta, and y star 1 minus beta by 1 minus alpha beta. This is the coexistence equilibrium point, and this is the E0 is 0, 0 is the trivial equilibrium point. Obviously, this coexistence equilibrium point star is visible, that is exist, if obviously x star greater than 0 and y star greater than 0, because it's a biomathematical model, biomathematical basis model. So x star obviously positive and y star positive. So from the values of x star and y star, we get alpha is less than 1 and beta is less than 1, or alpha is greater than 1 and beta is greater than 1. Because when alpha is less than 1, then this alpha is less than 1, so 1 minus alpha is positive, and beta is less than 1, so 1 minus beta is also positive, and obviously 1 minus alpha beta also positive, so x star is obviously positive and y star is also positive. If alpha greater than 1, beta greater than 1, then 1 minus alpha is negative and 1 minus beta is negative, and 1 minus alpha beta obviously negative, so negative by negative obviously positive, x star is also positive. So star is visible when alpha is less than 1, beta is less than 1, or alpha greater than 1 and beta greater than 1. Now let fxy equal to x into 1 minus x minus alpha y, and gxy equal to rho into y, 1 minus y minus beta x. This fxy is dx dt equals to fxy and dy dt equal to dxy. Next we find partial derivatives with respect to x and y. So del f del x, that is fx, equals to 1 minus 2x minus alpha y, and del f del y, that is fy, equal to minus alpha x, and del g del x, that is dx, equals to minus rho beta y, and del g del y equal to gy equal to rho into 1 minus 2y minus beta x. Then the Jacobian matrix J equal to fx fy gx gy. So 1 minus 2x minus alpha y minus alpha x minus rho beta y, rho into 1 minus 2y minus beta x. Then the value of Jacobian at the point x star y star, coexisting equilibrium point, then we put x star and y star in place of x and y, so we get this. Since x star y star is the equilibrium point, so this x star y star satisfies this equation, 1 minus x star minus alpha y star equal to 0, and from this we get 1 minus alpha y star equal to x star. So 1 minus alpha y star equal to x star, so minus x, this x star minus 2x star, that is equal to minus x star, and this minus alpha x star, and from this rho beta y star, and from this equation this 1 minus y star minus beta x star equals to 0. So 1 minus beta x star equal to y star, so put here 1 minus beta x star equal to y star, so y star minus 2y star equal to minus y star into rho, so rho minus y star. Obviously, trace of this Jacobian at this point x star y star is the diagonal matrix, principal diagonal addition of the principal diagonal matrix. So minus x star minus rho y star is negative, because x star is positive, y star positive, rho is positive, so obviously this trace is negative. And determinant value of this j x star y star equals to this into this minus this into this, so obviously rho x star y star minus rho alpha beta x star y star. Then taking common rho x star y star bracket 1 minus alpha beta. Obviously this quantity is positive, if alpha is less than 1, beta is less than 1. Because if alpha is less than 1 and beta is less than 1, then 1 minus alpha beta is positive and rho is positive, x star is positive, y star positive. So obviously this quantity is positive when alpha is less than 1, beta is less than 1. And this is negative if alpha is greater than 1 and beta is greater than 1. Then this 1 minus alpha beta is negative, and obviously determinant of the g at the point x star y star obviously negative. Obviously we get from because trace is negative and determinant is positive. So for this determinant value is positive. So this equilibrium point star is locally asymptotically stable for alpha less than 1 and beta less than 1. And this trace is negative, determinant value is negative, then this is unstable. This unstable equilibrium point star if alpha is greater than 1, beta is greater than 1. Next, question 3. Now, coexistence equilibrium point star, that is interior equilibrium point, does not exist if alpha greater than 1, beta less than 1, or if alpha less than 1, beta greater than 1. Because if alpha is greater than 1, alpha is greater than 1, beta less than 1, alpha is greater than 1. So this alpha is greater than 1, alpha is greater than 1. So 1 minus alpha is negative, and beta is less than 1. So alpha is greater than 1, beta is negative. So this alpha, so this is value alpha is greater than 1, beta is less than 1. Alpha is less than 1. So suppose half. So alpha is less than 1. Alpha is less than alpha. Sorry, alpha is greater than 1. Beta less than 1. Alpha is greater than 1. So alpha equal to 2. Say alpha equal to 2, and beta equal to half. So alpha equal to 2. So 1 minus 2 is negative, and 2 and half, beta half. So this quantity is 0. Denominator is 0. So this is undefined. And similarly, either positive, negative, alpha is 1 by 2. This is 1 minus the positive, this is negative, greater than 1. So negative, positive. So x star is negative. So in this case, when alpha is greater than 1, beta is less than 1, coexisting equilibrium point does not exist. Or in this case, alpha is less than 1, beta greater than 1, then also coexistence point star does not exist. In this case, Jacobian J is this. So we find the value of J at the point trivial equilibrium point 0, 0. So put x equal to 0, y equal to 0. So we get J at the point 0, 0, 1, 0, 0 rho. Obviously, this is the diagonal elements, principal diagonal elements, the eigenvalues 1 and rho. 1 is positive, rho is also positive constant. So obviously, eigenvalues are positive. So this equilibrium point 0, 0 is an unstable node. Unstable node. Now, J at the point 1, 0, this 1, 0, for this 1, 0, put x equals to 1 and y equal to 0 in this Jacobian. So we get minus 1 minus alpha, 0, rho into 1 minus beta. Obviously is lower triangular matrix. So upper triangular matrix is 0. So this is the diagonal elements are the eigenvalues. So minus 1 and rho into 1 minus beta are two eigenvalues of this. Obviously minus 1 is negative eigenvalue and rho positive. 1 minus beta, 1 minus beta, if beta is negative, if beta is greater than 1. Obviously, this beta is greater than 1, then rho into 1 minus beta is negative. So both eigenvalues are negative. So 1, 0 equilibrium point is stable node for beta greater than 1. If beta is less than 1, this is positive. Rho into 1 minus beta is positive. So this is negative and this is positive. So 1, 0 equilibrium point is saddle point if beta is less than 1. Next, Jacobian at the point 0, 1, E2, point E2, equilibrium point E2. So we get put x equals to 0 and y equal to 1 in this Jacobian matrix. So we get 1 minus alpha 0, 1 minus beta rho minus rho. Obviously, this is lower triangular matrix. So these eigenvalues are minus rho and 1 minus alpha. Rho is positive quantity, so minus rho is negative quantity, and 1 minus alpha is negative if alpha is greater than 1. So both eigenvalues are negative. So 1, 0 equilibrium point, that is E2 equilibrium point, is stable node if alpha is greater than 1. And this minus rho is negative and 1 minus alpha is positive if alpha is less than 1. Then this E201 equilibrium point is a saddle node for alpha less than 1. So we get if alpha is greater than 1, beta is less than 1. Obviously, E0 is unstable because E0 is unstable in all cases, and E1 is stable node because E1 is stable node. E1 is stable. If beta is greater than 1, beta is greater than 1, E1 1 0 stable. So beta is greater than 1, so E1 is stable node. And alpha is less than 1, then E2 0 1 is saddle point, that is unstable. And in this case, obviously, coexistence equilibrium point x star y star, that is E star, does not exist. And this case, or alpha greater than 1, beta less than 1, E0 unstable, E1 is saddle point, is unstable because alpha beta is less than 1. For beta is less than 1, E1 is saddle point, and E2 is a stable node for alpha greater than 1, E2 is a stable node, and E star does not exist. So we draw this figure 1. First case, alpha is less than 1, beta is less than 1. So alpha is less than 1, beta is less than 1. Then E0 is unstable. E star is locally asymptotically stable. We already deduced that this when alpha is less than 1, beta is less than 1, E star, x star, y star is locally asymptotically stable. So here E star locally asymptotically stable. And when alpha is less than 1, beta is less than 1, E10 is a saddle point. Alpha is less than 1 because alpha is less than 1. E2 is a saddle point, and beta is less than 1. E1 is also saddle point. Both are unstable. So we draw these two straight lines, this x-axis, this y-axis. We consider only the first quadrant because the mathematical model 1 minus x minus alpha equal to 0. We write this equation x by a plus y by b equal to 1. So we get this straight line passes to the point 1 0 and 0 1 by alpha. 1 0 is this point E1, and 0 1 by alpha. So this 0 1 by alpha and this point E10, this is the straight line represents 1 minus x minus alpha y equal to 0. Because alpha is less than 1. So this point is 0 1. So obviously 1 minus alpha is greater than 1. So this point 0 1 by alpha above the point E2 in the y-axis. And beta is less than 1. So 1 by beta is greater than 1. So obviously 1 by beta, 0 is right hand side of the point 1 0 point. And similarly 1 minus y minus beta x equals to 0. Writing in x by a plus y by b equals to 1 form. So this equation joining the two points 1 by beta 0 and 0 1, this E2 point 0 1 gives the straight line 1 minus y minus beta x equals to 0. And this from this here E0 are unstable, so trajectories are E1 is unstable, so this is unstable, and this is unstable, and this E star coexistent point, intermediate equilibrium point, this E star is stable, locally asymptotically stable. So all trajectories going to this point E star with t tends to infinity, time tends to infinity, and E0 is also unstable. Here E1 is unstable, E1 is unstable, E2 is unstable, and only inter equilibrium point E star is stable here. With time t tends to infinity, then both densities x star and y star exist and stable. And for this, next, if alpha greater than 1 and beta greater than 1, we get alpha greater than 1, beta greater than 1. So E0 unstable, E1 0 is stable, E2 0 is stable because alpha is greater than 1, E2 is stable, beta is beta is greater than 1, E1 is also stable. So alpha greater than 1, beta, figure 2, alpha greater than 1, beta greater than 1. So E1 is stable, E2 is stable node, E0 unstable always, and this star is unstable because already we deduced that Jacobian t is less than 0 and the Jacobian is less than 0. Sorry, determinant of this Jacobian star is less than 0. So this is unstable for alpha greater than 1, beta greater than 1. So we get this star is unstable, E1 is stable, E2 is stable, and 0, trivial equilibrium also unstable. So all trajectories goes to the point E2, 10 with time t tends to infinity, and all trajectories goes to the point 10. This. So this uh, picture graph shows that this 0 is unstable, and this E star is also unstable. That is actually saddle point. This, but this E2 and E1 is the stable node. And the third figure, from the third figure, when alpha greater than 1, beta less than 1, alpha greater than 1, beta less than 1, then alpha greater than 1, beta less than 1, E0 is unstable, E1 is saddle point, E2 is saddle node, stable node, E1 is saddle point, that is unstable, E star does not exist because E star is the intersecting point of this straight line, but this is the no intersecting point here. There is no intersecting point here. This 1 minus x minus alpha equal to 0, and this 1 minus beta x minus y equal to 0. So here this E1 and this is the E2. Here E1 is a saddle node. E1 is saddle node. So this trajectory goes to the point E2 from this saddle node, and this E0, that is 0 is also unstable, goes to the to E2, and all trajectories goes to E2 with time t tends to infinity. So from this diagram, this all species 1, species 1 uh, extinct, and the species 2 goes to the carrying capacity this, so species 2 exists for this case. And third, last case, alpha is less than 1, beta is greater than 1. So in this case, E0 unstable, E1 is stable, E2 is saddle point unstable, and E star does not exist. So in this case also there is no intersecting point, so E star does not exist, obviously no intersecting equilibrium point, and this E1, E2, E2, 0, 1, and this E1, 1, 0. And since E2, E1 is stable, so all trajectories goes to the point E1, with time t tends to infinity. And so from figure 3, the species 1 will go extinct, that is destroy, because here this E1 is unstable. So all species goes to the stable node this. So E2 is stable, E2 is stable, 0, 1 is stable. So this is the for second species, and this is for the first species. X-axis is for the first species, and Y-axis is for the second species. So from figure 3, the species 1 will go extinct, destroy with time, and the species 2 will approach its carrying capacity, and this point is carrying capacity, goes to the point carrying capacity. And from figure 4, when alpha less than 1, beta greater than 1, the species 2 goes extinct. Species 2 goes extinct because this is unstable, so all trajectories goes to the point E1. So species 1 approaches its carrying capacity. Now we draw the page portrait this. Here dx equals to x1 minus x minus alpha into y. Here alpha is less than 1, and dy dt is equal to rho is 2 into y into 1 minus y into beta into x. Here beta is less than 1. So alpha is less than 1, beta is less than 1. So this is the figure case 1. Figure 1. Alpha is less than 1, beta is less than 1. So we draw the first quadrant, this 0.0, and this 1.1, and this 0.1, that is actually 1, 0, that is E1, and this 0, 1 point, this is the point 0, 1 point, E2 point. So alpha is less than 1, this zero point 0.5, and beta is zero point 0.5. So alpha is less than 1, beta is less than 1. We draw the phase portrait for this is the direction vector for the trajectories. We uh, can draw from any point, click on the any point on this graph, we get infinite number of trajectories actually. So this point is E star. This E star is locally asymptotically stable. And this point is E2, that is 0, 1. 0, 1 is the saddle point. And this E1, that is 1, 0, is also saddle point. And this origin is also unstable. So all trajectories goes to the point E star, X star, Y star, X star, Y star for this case. And similarly, we can draw when alpha is greater than 1, beta is greater than 1. So put here alpha is greater than 1, 1.5, and beta is greater than 1, 1.5. So here, second case, alpha is greater than 1, 1.5 say, and beta is 1.5 say. So here we draw the trajectories. So all trajectories goes, all trajectory go to the point 1, 0, because 1, 0 is a stable node for the case alpha greater than 1, beta greater than 1. Also, this 1, 0, 1, this 0, 1, the E2 point, equilibrium point is also a stable node, also stable node here when alpha greater than 1, beta greater than 1. But E star is this point E star is unstable, unstable because all trajectories goes to the point this E2 or goes to the point E1, and is also 0, 0 is also unstable, unstable, and E star is also unstable. Actually, unstable E star also unstable. So this next case alpha greater than 1. So alpha equal to 1.5 and beta is less than 1. Beta is less than 1, say 0.5. So all trajectories goes go to the point 0, 1 E2. So here E2 is stable node. E2 is stable node, but this 1, 0, that is E1 is E1 is saddle point, that is unstable, and this 0, 0 is also unstable. 0, 0 is also unstable, 1, 0 is also unstable, and but 0, 1 is stable node. And the E star coexistent equilibrium does not exist in this case when alpha is greater than 1, beta less than 1. So in this case, first phase is dying out, but second phase is goes to its carrying capacity. Here, 1. Here, 1 non-Sledge quantity. And the fourth case, when alpha is less than 1, so put here alpha equal to 0.5 and beta is greater than 1, so 1.5. Next, we draw the trajectories. So obviously, trajectories, all trajectories go to the equilibrium point 1, 0, E10, and obviously this 0, 1, E2 is unstable saddle point, 0, 0 is also unstable, and E star does not exist here. So obviously, in this case, basis 1 goes to its carrying capacity, but basis 2 along the y-axis is dying out. Will go extinct for species 2. Next question. Population in competitive competition. Describe the two basic specific Lotka Volterra competition model. So already we discussed these equations. So here similar type dn1 dt is equal to this n1 zero growth isoclines is that is dn1 dt. This d1 dt means n1 equals 0 and k1 minus n1 minus alpha 1 to n2 equal to 0. This n10 growth isoclines and n2 zero growth isoclines null clines, that is dn2 dt equal to 0. So dn2 dt equal to 0 gives n2 equal to 0. So this equals to 0. So either n2 equals to 0 or k2 minus n2 minus alpha 2 1 n1 into 0. So obviously this axis is n1, this axis is n2. So from n1 equals to 0, so n1 equals to 0, this is the n2 axis, n1 equals to 0. And this n1 equal to k1 minus alpha 1 to n2. So we get this straight line in n1 into plane. So obviously this straight line is this. This straight line is this. dn n1 dt equals to 0. So obviously dn dt equals to 0 means, so this the vertical component of this velocity, this vertical component of the velocity is n1 k1 minus alpha 1 is equal to 0, because here dn1 dt equals to 0. So dn1 equal to dt equals to 0 gives this in n1 zero growth isoclines, n1 zero growth isoclines. So only vertical component upward or downward arrow here on this straight line. This is the dashes line. This is the n1 growth isoclines. This n1 growth and also zero growth isoclines, and this is the dotted line n1 equals to 0 and n1 equal to k1 minus alpha 1 to n2. This. And for the n2 zero growth isoclines, n2 equal to 0. So we solid line, draw this n2 equal to 0, this solid line, and n2 equal to k2 minus alpha 2 1 n1 equal to 0. This is the solid line this. So here n2 growth is 0. n2 zero growth isoclines means the isoclines is the horizontal. This movement on this point on this line is horizontal or right side or left side, horizontal movement here on this line. So we get these zero growth isoclines here. The below the graph of the line, figure 1, below the graph of the line, this below the graph of the line, that is when n1 minus k1 plus alpha 1 to n2 is less than 0. When this below, for this below, so when this less than 0, actually this equals to 0 when point on this line, and when on below on this line this is less than 0, this n minus k1 plus alpha 1 to n2 is less than 0, the region is this below of this line, and this greater than 0, this upper portion of this line. So this less than 0, so less than 0, then dn dt dn1 dt d1 dt is less than 0, d1 dt less than 0 by 2.1. So k in k1 n1 minus alpha 1 2 into greater than 0. Obviously dn dt is less than 0, so obviously this less than 0, but so this greater than 0, this greater than 0, dn dt less than 0, dn1 dt less than 0. In this case n1 increases and above this line n2 increases. So n1 increases, this n1 increases, so right side arrow, and above this line n2 decreases. Similarly n2 decreases. Similarly below the line 4, n2 increases. Below the line 4, this is the 4, this is the second line. Below the line 4, this n2 increases. Similar way above this n2 decreases, and n2 decreases, so n2 decreases is this downward arrow. Now, H portrait, one of the zero growth isoclines, N1 equals to this and N2 equals to this, may lie entirely above the other or they may intersect. We have four cases depending on the relative positions of N1 and 2 intercepts of these two isoclines. First case, case 1, N1 equals to Q1 minus alpha 1 to N2. This N1 by Q1 plus N2 by Q1 by alpha 1 equals to 1. And second line, N2 equal to K2 minus alpha 2 1 N1. That is N1 by this plus N2 by this equals to 1. If each intercepts of the line 5.2 is greater than the corresponding intercept of that for 5.1, so K2 by alpha 1 2 is greater than K1 and K2 is greater than K1 by alpha 1 2. That is, alpha 1 2 is less than K2 by K1 and alpha 1 2 is greater than K1 by K2. So we draw this line when this point K2, this N1 axis and N2 axis 0, this K1 is greater than K1 is greater than Q1 by alpha 1 2 and sorry K2 K1 by alpha 1 2 less than K2 and K1 is less than K2 by alpha 2 1, this point. So obviously this N2 rapidly excludes N1. Thus, if species 2 has a relatively large effect on the species 1, we expect that the species 1 will go extinct and the species 2 will approach its carrying capacity K2. This second species, N2 species, goes to K2 carrying capacity. And similarly, other cases, and case 2, when this case here, this species 2 is goes to extinct and the species 1 approaches its carrying capacity is when this case. And third case, if alpha 1 2 greater than Q1 by Q2, that is, and alpha 2 1 is greater than Q2 by Q1, in this case, we get this. So here, K2 and K1, that is actually K1 0, comma 0, and this is the 0, comma K2. Here, both are the stable. So all trajectories goes to this point and this point. So the coexistence point exist here. Equilibrium point K1 0 and 0 K2 are now both stable nodes. One or other of the species will go extinct depending on the initial condition. Case 4, when K2 is less than K1 by alpha 1 2, K2 is less than K1 by alpha 1 2, so K2 is below of this K1 by alpha 1 2, and K1 is less than K2 by alpha 1 2, K1 is less than K2 by alpha 1 2. So we then also these equilibrium points, this K2 0 K2 and K1 0 also unstable here, several point, and trajectories are drawn towards the stable node in the interior of the first quadrant. This is the intersection of this coexistence equilibrium point. Thank you. We complete this model here now.